Hi everyone, welcome to week 7. This is Luigi Renzullo here, giving you the first of 2 lectures this week, this one being on atmospheric circulation. Today's topic covers the large-scale motion of the atmosphere in the vertical, namely the atmospheric circulation patterns we observe. What happens when airflow resulting from equalization of atmospheric pressure meet or move apart, the convergence or divergence, as well as the large-scale patterns we see in the surface winds across the globe, the prevailing winds, and the mysterious force that drives the patterns we observe, namely Coriolis. Well, it shouldn't be too much of a surprise to you by now that the sun powers our weather and climate and drives our large-scale motion of, just drives the motion of the atmosphere in general. By now you will have recognized the number of 1365 watts per square meter as relating to the solar constant. That's the solar energy output at the top of Earth's atmosphere. But we know the Earth is a sphere, and while the sun power comes to us in parallel lines, its distribution across the Earth's surface varies in intensity. Namely, the power output over the equatorial region is more concentrated because the same radiation is spread over a smaller area than at, say, the poles, where the same radiation is spread over a greater area. So this means basically we get more intense solar heating at the equator than at the poles. But we've seen in our tutorial of last week that the Earth goes around the sun, and more importantly, the tilt of the Earth's rotation, the axis of rotation compared to the plane of the orbit of the sun, drives our seasons. And what we observe on the Earth's surface is the migration of the sun north and south in the sky over the year, giving us our seasons. So that area of intense heating through energy output of the sun on the Earth's surface will move north and south depending on what the seasons is. And this graphic just shows that in January, for example, the top left, we have more intense heating south of the equator. Then as we move through the seasons, autumn, top right, winter, bottom left, and then spring time, bottom right, we see that concentration move about the equator in north-south direction. So just stepping right back, you should hopefully know by now, convective heating is when we have energy input to a gas or fluid. That energy leads to a decrease in the density of the overlying fluid. So if we consider this pot, for example, of water, the heat from the gas burner heats up the fluid. The fluid immediately in contact with the heating source, it becomes less dense. Now we all know from our last week's work that less dense fluids will rise above more dense fluids. So less dense, warmer fluids rise above more dense, cooler fluids. But more importantly is that this leads to a current, a convection current, and that circular pattern is what we call a convection cell. So in our case, with the solar radiation, we have solar radiation as the energy input to the surface. That surface then re-radiates the overlying air above it, leading to the convection processes that expand or reduce the density of the overlying air, warming it, and that air will rise above the surrounding cooler air. This gives rise to the circulation patterns. And when in 1735, George Hadley was trying to come up with a model for the distribution of energy across the globe, he proposed this single cell model of atmospheric circulation. So he made some assumptions, however, that the globe is a uniform surface, so there's no variation in the surface of the globe. that it is a static sphere, it's not rotating, and it's the variations in pressure from the poles to the equator that drive the prevailing winds. Now, we'll come back to the winds in a minute, but just here, let's consider that this model takes the solar heating at the equator. That more intense solar heating drives convective processes, lowering the density of the overlying air. Less dense air will rise and form a cell. Now, as that air rises, it then begins to cool, moving away from the equator, and it starts to descend and settle at the poles. Now, rising air exerts less pressure on the surface, so we have that heating resulting in a low pressure system. Over the poles, however, where we've got the descending air, the air is descending because it's cooler, becoming more dense. As it descends, it exerts a pressure on the surface. The resulting pressure there is a high pressure. So this is an example of that convection cell, single cell model describing the large scale variation in circulation proposed by Hadley. So we also displayed here is this idea of the surface flow for going from the poles to the equator. Where does this flow come from? So we'll just pause and step back. I hope that you understand the idea of gradients. Here we have two balls on top of two very different gradients. On the left, we have what we call a shallow, weak gradient. The slope of that ramp is less than the one on the right, where the slope is steeper. It represents a strong gradient. Now, under gravity, hopefully it's not too surprising that the contribution of the force of gravity on the ball will make the ball on the right go down the slope faster than the ball on the left. So the greater slope or the stronger gradient the ball will move faster down the slope than the ball on the left, where the gradient is weaker. So too in the pressure environment. So in a pressure environment, we have the equalization of pressure going from high to low. That's just a fundamental rule that you should become familiar with. Pressure equalizes from a region of high pressure to low pressure. There is a flow of air from high to low. On the left here, we have an example of a weak pressure gradient. You can think of these as contours on a contour map, for example. On the right, we have an example of a high pressure to low pressure system where the gradient between the high pressure and the low pressure system is a lot stronger, a steeper gradient, and the equalization exerts a stronger force. The flow of air from high to low in the bottom right example is faster than on the left, where the gradient is less. So here we're depicting by concentric circles this idea of gradient. The tighter the spacing between the circles, the steeper the gradient, the stronger the equalizing force. This is the pressure gradient force. So in a pressure gradient force, air moves from areas of high pressure to low pressure. The greater the difference in pressure between the two areas, the stronger the pressure gradient force. The stronger the force, the stronger the winds in our case. So we will see in subsequent parts of the lecture and next lecture as well, the idea of these surface pressure maps, the synoptic maps that you might be familiar with looking at the Bureau's website, regions of high and low pressure, and the contours displayed on these maps indicating the sort of strength of the winds in the area. So pressure gradient forces flow out of the high pressure and into a low pressure environment. Movement of air horizontally under pressure gradient force from high to low is referred to as advection, and this is more commonly known to you as wind. And a measure of wind speed is given by an anemometer. These are a series of cups on a rod. They will rotate with moving wind. The faster the rotation, the stronger the wind, and it's a way of measuring wind speed. The arrow on the right is a measure of wind direction. Those two things combined are a useful source of predicting the flow of air from one area to another. Okay, so here's a schematic of the idea of the circulation pattern. We have a surface, hot, heated surface, heating the air above it, that air rising because it's less dense than its surrounds. So that rising air leads to that convection. As the rising air gets to the top of the atmosphere, it starts to cool, and then it starts to descend on the descending lobes, leading to this circulation. And the warm, less dense air exerting a low pressure on the surface, whereas the cooler, more dense air sinking exerts a high pressure. Now, we've just talked about pressure gradients force, so it shouldn't be too surprising then that there is a air flow from high to low. This is what we'd experience as wind on the surface. I'll also just mention at this point that this idea of nature abhorring a vacuum. I can't remember who said that, but this idea that what tends to happen if natural processes try to make a vacuum, like move mass from one area to another, something will rush in to fill the void. So in this case, you can imagine the ascending air creating a bit of a void, and air from the surroundings will rush in to fill the gap. So that air flow coming in to fill the gap left by the rising warm air. We talk about the air flow coming together and then moving apart. Those areas of where the wind goes from high to low, meeting at the high, this is areas of convergence. That lifting to the top of the atmosphere where the airflow moves apart to start this descending part of the cell, circulation cell. At that point where they move apart, that's where the airflow diverges, the divergence. And because we're talking about cycles, this can be repeated. So areas of air coming together is convergence. Areas of air moving apart is divergence. And we have similarly at the top of the atmosphere where the cooler air starts to descend, part of that circulation cell where the air is descending, it's cooler and it's getting more dense and descending. That airflow is converging to descend and create the high pressure on the Earth's surface. And where the high pressure, upon reaching the Earth's surface, the air warms and moves apart, it diverges. Right, so this was the model that we saw from George Hadley. But the problem is that this isn't what we observe when we look at major circulation patterns or airflow on the Earth. For starters, Earth is not a static sphere, it is a rotating sphere. And what has subsequently been proposed is a 3-cell model that fits a lot better with what we observe with regard to the large-scale vertical motion and the horizontal winds. So this 3-cell model, starting at the equator, we have, in honor, I guess, of George Hadley, we have the Hadley cell. This is where the intense heating at the equator results in that uplifting of warm, less dense air, creating a low pressure. The circulation descending around about the 30 degrees in latitude mark. And that cell, we've got one either side of the equator, is called the Hadley cell. So then from the sub 30-degree latitude mark, right up to about 60 degrees, we've got that diverging airflow where the high pressure system sits over that 30 degrees latitude, moving towards the poles, and then meeting some other heating and lifting to create another low pressure system. And that cell between 30 and 60 degrees in latitude is the Farrell cell. And then we see a final cell from 60 to the poles, degrees in latitude to the poles, as the polar cells.